Okay, let's take a look at this question. Here we have a buffer that is made out of a weak acid, acetic acid, and the salt of the weak acid, which is sodium acetate. So here, sodium acetate, when it dissolves in water, it will dissociate to form CH3COO-, that's the acetate ion, and Na+. So before we start any calculations, let me write out the dissociation reaction for acetic acid. So CH3COOH will react with water to form CH3COO- and H3O+. So from this reaction, I hope you can see that acetic acid is the weak acid and acetate is actually the conjugate base of acetic acid. So first, the question is asking you for the pH of the starting buffer. So this is pretty straightforward. For buffers, to calculate pH, we can use the Henderson-Hasselbalch equation. That's pH equals pKa plus log base. In this case, the base is acetate over acid. So that's acetic acid. Alright, so here we have Ka, and pKa will be negative log Ka. We are also given the concentrations of acetate and acetic acid, so let's just sub that right in. So the pH of our buffer is 4.77. Now let's look at what happens when you add some NaOH to the solution. So now you are adding a strong base to the solution. This strong base is going to react with the acid that's in the solution. So in the buffer solution, we have acetate ion, which is the conjugate base, and we have acetic acid, which is the weak acid. So NaOH is going to react with the weak acid, that is acetic acid. So let's write the reaction that happens. NaOH is going to dissociate to give Na plus and OH minus. So let me just write the reaction between acetic acid and OH minus. So here we see that acetic acid is going to react with OH minus from NaOH to form the acetate ion. This is an irreversible reaction, again because NaOH is a strong base. So as long as you have either a strong acid or strong base in this acid-base reaction, it is going to be an irreversible reaction. In order to calculate the pH after addition of NaOH, we need to find out what are the new concentrations of acetic acid and acetate ion in the buffer solution. This is so that we can sub the values into the Henderson-Hasselbalch equation. But instead of calculating concentrations, we will be calculating in moles so that it's easier to do the calculations. So let's first take a look at the initial number of moles for acetic acid and the acetate ion. Okay, we are given that the initial concentration of acetic acid is 1.01 molar and the volume of the buffer solution is 1 liter. So number of moles would be concentration times volume. And similarly for the acetate ion, you are given that the concentration was 1.07, and again the volume of the buffer is 1 liter. Now we can look at the change, which is basically the number of moles of NaOH. Okay, so we don't have to calculate this because it's already given to us that the number of moles of NaOH added is 0.07 moles. Okay, so now we can find out the final number of moles. For acetic acid, initially you have 1.01 moles, but 0.07 moles has reacted with OH minus because it reacts in a 1:1 mole ratio. So now we have 0.94 moles. And as for the acetate ion, initially we have 1.07 moles, but now the moles have increased because more acetate ion is being formed. And you have an increase of 0.07 moles. So now we have 1.14 moles of acetate ion. Okay, so now with this new number of moles of acetic acid and acetate ion, we can sub these values into the Henderson-Hasselbalch equation. The volume is 1 liter. So now we have a pH of 4.83. Now in part C, you have a further addition of HCl to this buffer solution. So when you add HCl, HCl is going to completely dissociate to give you H plus and Cl minus. Okay, and so H plus, which is an acid, will react with the base that is in the solution. So between acetic acid and the acetate ion, the base would be acetate ion. So let's first write out the reaction that happens between acetate ion and HCl. So again, you see that this is an irreversible reaction because HCl is a strong acid. So whenever there's a strong acid or strong base in the acid-base reaction, it is going to be an irreversible reaction. Now let's look at what are our initial values for acetate ion and acetic acid. Okay, we actually know from the previous part B, that we have 1.14 moles of acetate and 0.94 moles of acetic acid. So let's write that down. Okay, then let's also look at how much HCl is added. For this one, we don't need to calculate because it is already stated that the number of moles of HCl added is 0.118. So acetate reacts with H plus in a 1:1 mole ratio, so we can find out what is the final number of moles. by taking the initial number of moles minus the number of moles that reacted with H+. And similarly for acetic acid, we initially had 0.94 moles, but now we are adding more acetic acid because more of it is formed. So there is 0.118 moles that is formed. And now we have 1.058 moles of acetic acid. So with these values, we can now sub them into the Henderson-Hasselbalch equation to get the pH. Again, the volume is 1 liters. So you have moles of acetate over 1 liter divided by moles of acetic acid over 1 liter. So then you have your final answer, which is pH 4.73. My answers may be slightly different from the McGraw-Hill answers, but that's just a slight difference due to rounding.